Welcome to today's session. Today we are going to discuss electric field intensity and its application using blackboard and chalk piece. So far we have discussed this concept using PowerPoint presentations and 3D animations. Today we have to discuss very important derivation which is basis of entire electrostatics as well as magnetostatics. Once we understand this concept, how to derive the strength of signal in space. If we know the steps for one method, then we can do it for all other methods. So first one, electric field intensity. What is electric field intensity? Electric field means the electric force lines working in space, and we have to calculate its intensity. Like we have seen the example of mobile phone and the mobile tower. When we get electromagnetic wave which communicates from mobile to mobile, it is part of two signals. One is electric field, another one is magnetic field. So when we say our signal is good, that means the strength of signal is good. And what is that strength? That strength belongs to electric field or magnetic field. So this is what we have to calculate. So we have a mobile phone which uses antenna to transfer the signal outside the mobile phone. And what is an antenna? An open wire can also be an antenna. We use antennas in FM radios, we use antennas in transmission stations, we use antennas in mobile phones, and we have lot of applications of antennas. So these antennas are basically conductors. And what is function of conductor? The function of conductor is to move the charges from one place to another place. They are conducting the electrons. Now when we say electric field intensity, we have derived it from the Coulomb's law of forces. What is Coulomb's law? The force between two charges is given by product of two charges, and it is inversely proportional to 4 pi epsilon naught r square. Force is a vector quantity. So we have to add a bar on the head of force F, and we add one direction component which is given by AR cap. And electric field intensity, which is denoted by capital E, is nothing but force per charge. How much force we are applying per charge or group of charges. When it is an antenna or mobile phone, we can consider it as one point where number of charges are available, and someone from another antenna is applying force on those charges. So it is force per charge. So with our definition, electric field intensity is simply force per charge. So if I want to calculate force on any one charge, say Q2. So if I want to calculate this, so we have a formula for the force. So I will write down Q1 Q2 divided by 4 pi epsilon naught r square, say per Q2. So per Q2, if you write like this, what will happen? This Q2 and this Q2 will get cancelled. So the remaining term will be Q divided by 4 pi epsilon naught r square, and we can add the direction component AR cap. When we include the direction, we can add a bar on the head of E. That means now this is vector quantity. Electric field intensity is a vector quantity. Now this one is called as electric field intensity formula for a point charge Q. But we don't deal with a single charge, we deal with more number of charges. We call it as the density, like number of charges are present at one place. Now if we talk about this chalk piece, now in chalk piece we can resemble it with a conductor. If you have seen a wire, if you zoom out, what will be the exact shape of a conductor? Like a cylinder. And there will be number of charges present on that particular line. That means there is charge density. And which charge? Line charge. So we will call it as line charge density. So for distribution of electric field intensity, we may have various possible shapes. The electric field intensity may be due to line charge. So this line charge may be a conductor wire. So say this is a conductor of total length L, which is applying some kind of force on surrounding region. So, if my antenna is of this shape and I have to calculate how much force it is applying on any other point, then I will say that there are number of charges, source charges present on a line. So, the density of charges on this line will be denoted by rho L. So, we will write it as rho L, we will use rho L for line charge density. So, these are the charges present on a line. When we connect all charges in one after one, it will become line charge density. So, we have one possible condition of line charge density. Now, this line may have various shape. A wire can be molded, folded. So, there may be a circular shape of line. We can have a case where we may have a wire like this, or there may be a zigzag shape of line. So, all these cases where line is involved, and if there are charges present on that line, so we will consider the intensity of charges, the density of charges. Rho L will be density for line. Similarly, my surface may be a square shape, triangular shape, a plane, like there may be printed antenna. So, another possible shape where charges may present is a surface. So, another case we can have is surface charge density. So, one possible source is line charge, another possible source is surface. So, there may be some surface on which number of charges will be distributed. That means I have a sheet, on entire sheet there are charges distributed, and how we get these shapes? From a single point charge Q. When I connect number of Q's, I get a line. When I connect number of lines, I get a surface, and if my charges are present on surface, I will denote it with rho S. So, it will be termed as surface charge density. So, one thing is line charge density, second important thing is surface charge density. Now, like from point we got a line, from line we have surface. If we connect multiple surfaces, we will get a volume. My source, my antenna may be a volume. Volume may have different shape, it may be cubical shape. So, if I consider a third case where I want to calculate volume charge density. So, there may be a sample volume, say a cube of any shape, and on this cube there will be number of charges present. So, for this charge density, we will represent it as rho V, that is volume charge density. So, we have to calculate electric field intensity due to a line charge, due to a surface charge, and due to a volume charge density. And for point we have already defined. We have one formula which is already available for point charge. So, this one is electric field intensity due to a single point charge. In examination, we get questions to derive electric field intensity due to a particular type of charge distribution. So, we know we have three kind of charge distribution possibilities according to the shapes we can make. Now, what is there in this charge density? For this formula also we have to understand. For all the densities, intensity and density, these two things are very much related with each other. They are closely related with each other. Wherever there is density, there will be intensity. We say there is light intensity. At the same time, we can say there is light density. In a room, there may be various kind of distribution of light according to the source, according to the say windows, doors, and the availability of light sources. Light under tables and the corners, and where the light, there is some object which is stopping the light, there will be less density. Places where it is open to the windows, doors, and the light sources are available, their density will be more. Similarly, these electric and magnetic field intensity will also have various values with respect to space. We see that mobile signal strength is different in open area, it is different inside classroom, it is different in say any underground office or any underground place. It changes with respect to the obstacles. So there will be intensity and density varying with respect to space. Now how to calculate a line charge density, for example? It is the density of line charge. Always, all the densities, we will come across various densities throughout this subject. We have to remember a simple thing, that all the densities are directly related with the cause, the one who is creating the density, and they are always inversely proportional to the distance with their source. For example, this is line charge density. Who is creator of charge density? Charge. So it will be directly proportional to charge Q, and it will be inversely proportional to the length of this line. So it will be given by Q by L. Then if you talk about rho s is again surface charge density. So creator of surface charge density is also charge, because charge is creating charge density. So what can we say? Rho s is equal to again Q. For line, the length of line is considered. For surface, there will be surface area. So we can say rho s is equal to Q by S. So this is formula for surface charge density. Then next, volume. It is not only volume, this is volume charge density. So who is creator of this volume charge density? Again same charge, we are talking about charge distribution. So charge is creating charge density. So again it will be equal to Q. Now in this case we have to consider the volume. So it will be Q by V. So now we are clear about the formulas for charge densities. Now let us discuss why they are inversely proportional to the length, distance, their surface or volume. For that we will take one more example. So I will just rub this side. Now I want you to imagine one example. Imagine that you are holding a torch with a circular glass, and you are pointing it towards the green board. Okay, so we will have some torch, say like this. Say this is the torch you are holding in your hand, and the light will come out of this particular torch, and we are projecting it on a surface, say wall, at this place. Now if it is a circular glass, we will have a circular shape of light on this particular object. So now imagine you are holding a torch towards the blackboard, and there will be a light spot. That light spot will have some intensity and density. Now imagine that you are holding this torch and you are moving towards the wall. So what will happen? The area of that spotlight will decrease as you are going closer, but the brightness of light in that small area will increase. Are you getting the point? If you are going away, the area will increase, but the density will decrease. The light intensity will not have same value. It will not be that much strong. So as you go closer, the area decreases, but the density increases. So it is inversely proportional to the distance. If you consider light intensity, as the distance increases, the density decreases. As distance decreases, density increases. So it is inversely proportional to the length or its area or volume. So these are the charge distribution. Now we have to consider the cases one by one. So first case we will take electric field intensity due to line charge density. So I will just pause it for a while and I will rub it, and then we will continue for this line charge density. Now let us discuss the first condition of electric field intensity, where source is a line. So we will consider a wire, a conductor, as our source, a line which is present in space, and it is applying some force in the neighboring region. And we will take a sample charge who is facing that force, and we will calculate what is the strength of electric field on that particular place. Like you can imagine, you have one antenna and one mobile phone. Antenna is applying some strength and we have to calculate how much strength is available on that particular charge, that is force per charge. So, for that we will consider a coordinate system. We will draw 3 axes as usual. So, we have z, y and x axis. So, for reference we have to put our wire on any one axis. For simplicity of derivation, we will consider that our conductor is present on z axis. Say this is z axis, I am putting one wire on z axis and this is say some length L conductor. This is the source. So, we will call it as source who is applying force on some reference point. We have to consider some reference point. We will consider reference point is available on the floor. So, on z axis and one corner we have our conductor and on floor we have one charge. Say on this plane, xy plane, we have one point, say point Q or simply point P. Right, there is a charge on the floor. So, this entire line is applying some force on this charge. So, for calculation of the entire electric field intensity due to that entire wire, first we will take a differential source material and we will calculate differential electric field intensity on point. Once we have differential value, then we will integrate it and we can find out the entire electric field intensity. So, here we will consider small differential length on z axis. So, we will call it as say differential length for calculation purpose. Differential length is applying some charge on this point P. So, this distance is called as position vector r bar and differential length is applying some differential charge, say dq. So, we have differential length. Now, differential length is on z axis. So, we can call it as dz also. Already we have one formula for electric field intensity of point charge. It is given by E is equal to q upon 4 pi epsilon naught r square into ar cap if it is a vector. Now, dl is applying differential electric field intensity. So, we will write it as dE cap. Differential electric field intensity will have differential charge. So, this is the normal thing which we are using. From this we have to derive for line. So, for line, what is the charge? Charge is not a single charge dq. Charge is rho L, just now we have discussed. So, rho L formula is cos q per length L. Now, charge is differential charge. So, this one we can write as dq. Differential length is dl, which again on z axis. So, we are writing it as dz. So, from this we can say dq is equal to, so this from this equation we can say dq is equal to rho L dz. So, we can put this value in the place of dq. So, what will be the expression here? We will have dE is equal to rho L dz by 4 pi epsilon naught r square into ar cap. So, if you want the entire electric field intensity, what we have to do? We have to integrate it. What will be the limits? Limits are on the z axis. So, there may be length. If we consider that our conductor is starting at the origin where all 3 axes are 0 and the total length is L. So, the limits will be from 0 to L. There may be various limits also where there may be L1, L2. It depends on what length we are taking. So, what the modified formula may be for electric field intensity It can be given as integration for say some length 1 to length 2 rho L dz by 4 pi epsilon naught r square into AR cap. So, this is generalized formula for electric field intensity due to line charge distribution. Now, in line charge distribution, most commonly asked question is infinite line charge. Infinite line charge is applying electric field strength in the surrounding region, and we have to calculate what is that value. So, let us imagine that now this conductor is not having a finite length. It is extended from positive infinity on z axis to the negative infinity on negative z axis. So, my conductor is present all over the z axis to infinity. So, for that this part will be same. Now, what will be the change? Changes will come in the integration limits. So, again we can calculate the AR cap. The calculation of AR cap is a separate procedure. Now, we will understand, because calculation of AR cap and position vector is very important. In problems and examples also we have to follow these steps. So, how to calculate that? Let us now focus only on AR cap. What is AR cap? This is E bar, the vector. What is definition of vector? It is magnitude into direction. So, in this half part is magnitude. So, this is say magnitude and this is direction. It is also called as unit vector. We have to remember these names. So, this is unit vector or direction of this vector. So, we will take it out and we will focus on AR cap. So, this is AR cap. Now, vector is equal to magnitude into direction. So, what will be the direction? Direction will be equal to vector divided by the magnitude. So, what is AR cap? AR cap vector will be say r bar is its vector, the position vector r bar, this line, and it will be divided by the magnitude. So, this is r bar vector. So, all vectors are given by magnitude into direction. So, the direction will be equal to vector divided by magnitude. So, this formula we have to use to calculate the direction component or unit vector AR cap. Then we have to focus on r bar. We require r bar and mod of r bar. So, what is this r bar? R bar is a position vector which is connecting the source to destination. Either our line is finite or infinite. We are considering small differential source which is applying small differential electric field intensity on given point, and then we are integrating according to the requirement of our problem. So, this R is connection between source to destination. Destination is the one who is facing the force and source is the one who is applying the force. So, this line is applying the force and this point is facing the force. So, this is called as destination. In Coulomb's law example we have discussed, calculation of r bar is destination points minus source points. So, here we can write it as r bar is equal to destination points minus source points. Now, what are the destination points and source points? Here we have to consider one coordinate system. The shape of conductor is cylindrical. We are considering a wire is placed on z axis and the shape of a wire, if we zoom it, it is nothing but a cylindrical shape. So, we will consider cylindrical coordinate system. So, in cylindrical coordinate system we have three components. One is say r, another one is angle phi, and third one is height z. So, if I consider source and if I want to calculate the source points, So source points here on z axis, radius is 0. There is some noise outside. Just we'll pause for a minute. So let us briefly conclude this topic. Still we have some noise outside. So I will try to make it loud. So we want to calculate R bar source points where it is on z axis. On z axis radius is 0. We are starting on the line. So this one is place where radius is 0. There is some angle phi. We will consider phi, and of course there is height z. So source point will be 0, phi, z, and destination points. There is radius. So there will be r. There is angle phi, but there is no height z, because we are talking on the floor. From floor we start calculation. So floor where we put our foot, the place where z is 0. So destination points are r minus phi minus 0. So how we calculate r bar? R bar will be destination point minus source point. So this is r. R, we have to take the direction of r, which is ar cap, r ar cap minus 0, it will be same value. Then phi a phi cap minus phi a phi cap, it will be 0. Then 0 minus z a z cap, so it will be minus z a z cap. So this is our r bar. So what will be the mod of r bar? So here we will write r bar in this place. So ar cap can be given by, here I will write down, ar cap will be r bar, that is r ar cap minus z a z cap. If we take mod of r bar, so it will be square root of r square plus z square. So this is nothing but ar cap. So this ar cap we have to put in place of this ar cap. So once we write it here, put the limits, we can find out electric field intensity for infinite line charge. The further derivation we will continue in the next session. Till then you practice this derivation. Have a good day.